Contact models, right? There's my thing, my two things. Take out my pocket knife, make the hole. At that point, there's forces, maybe moments, update them. Relative motion, update them. That's the goal. This is just showing some stuff from the manual. It's just a local thing. This might be a clump. And really all that matters is the local. There's a contact. Look, it has a position in space. It has a local coordinate system. And it's between two surfaces actually. All right. So there's all sorts of contact models that are built into PFC, and we're just going to give a very high level overview. It's like we're flying in a 737 right now and looking down at the landscape. Oh, look at that. I see these different contact models in PFC. Some of them are models that allow you to do bonding. Those are the ones we're going to use when we do bonded particle modeling. Okay. We've talked about two of them, linear contact bond, linear parallel bond. Okay. There's also this one we call the soft bond, which basically is the parallel bond. This parallel bond model, if you think about it, it's like those little guys, those little things in between the glass beads, right? It's cement between the glass bead. And if you had cement between the glass beads, and if that cement was brittle, you would be able to, say you had two glass beads glued together in your hands, you could rotate them and twist them, and it would be elastic until boom, it would break brittly, and then it's gone. That's how the parallel bond is. It's a brittle failure. It's just gone. When it breaks, it's gone. What you could though say is you could say, okay, now when I glue those glass beads together, I'm going to put some a different type of adhesive such that when I stretch them, for example, it's going to reach a certain point and it's going to go elastic, perfectly plastic, and it'll slowly lose strength with increasing strain. We call that, if you have a stress strain curve that goes up and then it starts going down, but it doesn't go down brittly, we call that softening. So we have a more sophisticated parallel bond model that has softening, and we call that a soft bond model. It turns out that to represent various behaviors of grains of rock, we sometimes need to do that. Okay. Another way of doing different things with grains of rock is using this flat joint model, which we'll talk about. And then you may recall that picture I did where I have a rock mass, which is a base material of a bunch of grains, but then we overlay joints on that. And we have a special contact model that lets us put joints in so that the bumpiness is removed. So we call that a smooth joint model. Okay, and that also can be glued, if you will, bonded. The joint can have some cohesive strength to begin with, and then it can break free, and then it's frictional. That's the smooth joint. And then there's this, don't worry about adhesive rolling resistance model. Okay, that could be used, for example, oh, this is crazy. In your laser printer, in your black laser printer, there is powder in there, and that powder somehow gets deposited on the paper and melted. If you want to model the behavior of that powder, okay, it turns out that there are actually cohesive forces in that granular material. And it's because the powder is so small, there's electrical interaction and surface charges affecting that stuff. So it's basically a granular material that's sticky. One way to do that is using this thing called an adhesive rolling resistance model. Okay, that's all we're going to say about it. Now, we add some more stuff to here. So look at the difference. Look at this side. There's the bonded ones. There's the granular ones. If you're just doing a granular model, right? Linear, we talked about that. Kn, Ks friction. Hertz, we talked a little bit about that as well for doing granular systems. There's also this thing called a rolling resistance linear model for granular systems. We're going to talk about that in the next lecture, so we'll put that aside. The basic idea, though, is that particle shape is critically important to the behavior of a granular material. And spherical particles have very little interlock between them. Think of a spherical particle in the middle of a big assembly of spheres, and if you could reach in and rotate a sphere, there's no dilation. But if you had a grain of rice and you rotated that, there would be giant dilation, which means it's more interlocked. And there's a trick people have come up with that can make spheres behave as though they're interlocked, and it's called rolling resistance. So we'll talk about that later. And we're not going to talk much about it because the focus here is not on granular systems, it's on bonded systems. Just a couple funky ones here. This hysteretic model has a hysteretic curve. Remember, we got that naturally when we did the geogrid stuff, where we load up and we unload, and the curve goes up and bends over and then goes back, and it loses some energy because it doesn't go back to the same place it did before. That's a hysteretic energy loss. That might be something you do if you want to have a collision of particles and bouncing back, right? You might want to have, that would be the mechanism, you could say, is what's causing the energy loss. And then some people are also doing small strain viscous creep. There's a contact model called the Berger's contact model to do that, okay? And then the last one, you can write your own contact model. So we call this a user defined. You can write your own contact model, but you have to write it in C++. So it's, if you know C++, it's easy. If you don't, it might be a difficult challenge. And this is just an example from some years back of a person I worked with at the University of Minnesota, and he did modeling of carbon nanotubes. And basically what that is it's something at the scale of nanometers. You take a sheet of carbon, which looks like chicken wire, and you roll it up into a tube. And those are the carbon atoms, but now their carbon atoms are linked in a sheet, but the sheet's been rolled up into a tube. That's called a nanotube. If you take an assembly, a whole bunch of nanotubes, you get incredibly awesome material properties, like 80, hundreds of times stronger than steel, stuff like that. So people are interested in these nanotubes. And so this user-defined contact model allowed us to actually model a pile of nanotubes, where you take a collection of balls that are bonded. So it's just like the geogrid thing. So if you take a string of balls that are bonded, it behaves like a beam of circular cross section. And then what you do is you need to understand the physics of nanotubes, which is crazy. Think of this. I have a single nanotube. It looks like a pencil. It's vertical, sticking. I'm holding it in my left hand. I have another pencil that I'm holding in my right hand. I slowly start moving the pencil in my right hand towards the pencil in my left hand. When I get within about 3 diameters of the pencil, the guy on the left starts getting affected and starts moving, even though the guy on the right is not touching him. It's an interaction at a distance. It's black magic. What is it happening? Why are these guys interacting at a distance? I'm going to guide you. Now think of it, this is at the nanometer scale. There's crazy things start happening because we're used to thinking of the world at a much bigger scale. Remember your basic thing. Now this is something you would have learned in chemistry class when you were a freshman. They talk about atoms have this cloud of electrons flying around them, right? And this is why chemistry works, right? Because different atoms, they get close enough together and their electron clouds interact and they make other compounds, right? When you're at this scale, that nanotube has there's a cloud of electrons around it, and there's a cloud of electrons around the other one. When those electron clouds start interacting, they produce mechanical forces. These forces are also called van der Waals forces. And so this really happens. Like when I first heard this, it was like, this is crazy, right? So then the question is, so in 2010, this professor from Minnesota came to talk to me and said, could we model carbon nanotube interactions with PFC? And I said, yeah, of course we can. And he was like, no way, how could you do it? And I said, here's what you could do. You could take each particle, those are the big guys that are glued up together in a string, and you could tell PFC, you could say, okay, I'm going to give you a fixed distance, which is 3 diameters of that thing. And I'm going to tell you, PFC, that anytime a particle gets that close to another particle, I want you to create a contact between them. So you start running PFC. As soon as one guy gets within 3 diameters of another, all these contacts form. Okay. Now, because I have a contact, right, I can start applying forces on the 2 interacting guys. And so you can work out for these nanotubes, given the orientation of a certain chunk of one and a certain chunk of the other, what that interaction force is. And so what you do is you work out that interaction force for just a little chunk and another little chunk. And then you just say, okay, well, every single particle now, when it starts getting next to another one for any reason, it starts doing that interaction force. And so then you can now do anything. You can take a pile of these things and they will interact appropriately based on this force. And so there's a lot of work that this professor, this Dimitrika guy, has done since that time with a number of grad students where they use PFC 3D to simulate the interaction of these carbon nanotubes. It's a good, interesting example of the idea that, when I say any system that can be described by particles that interact with one another could be modeled with this type of an approach. So that's all I'll say at this point, but I'm using that to demonstrate that you can write your own contact model, and sometimes that might be necessary. Oh my God, look, there's even more built-in contact models. This is kind of like Abacus, finite element programming, constitutive models, right? The original version of Abacus and way back probably had like 3 constitutive models, and now it probably has 70. I don't know. So there's a few more. There's this to do magnetization between 2 particles. That's this dipole model, right? At this point, we even have a van der Waals thing built in as a contact model. We didn't have that in 2013. That's why that guy had to write his own contact model. Again, history to penelastoplastic, oh my God, all kinds of crazy stuff. Then we have this one. This is a relatively new idea of how to build a bonded particle model. And we call this a lattice model. And I will talk about this and show you some results for it when we talk about bonded particle modeling. This is a relatively new thing in the last maybe 3 years. And this particular type of bonded particle model is superior to all previous bonded particle models. I've been doing research with it, and it's behaving better than my wildest dreams. So we'll talk a little bit about this. Okay, that's all I'm going to say for now. Well, hold on. I'm going to show you a picture of as a precursor to that, which some of you may have seen because I might have sent this before to some of you. This is this subspring network model. These are Voronoi cells joined together with this special contact model, and that's trying to represent the grain structure of something like a granite. All right.
So in
That's
that
how we're
case, that's going to be zero porosities, right?
Exactly. We would refer to this as a bonded block model, has zero porosity, perfectly filled space. And that's part of the idea here. The granite is essentially a perfect zero porosity thing. It has super tiny micro cracks, but the porosity of this granite is super small. That's all I'm going to say now on that. Just a minute right there. We're almost done. Van der Waals. Last thing to say about the physics. This is something that every discrete element program should have, and we do have it in PFC. The question is, since there's all these different contact models, whenever a contact forms, the code needs to know what contact model to put in, and it also needs to know what properties of that contact model to assign. Just think about it, because it's running in the background. The code's running. New contacts are forming. What are you supposed to do? So what we have is we have this thing called the contact model assignment table, CMAT. So there's a command, CMAT, blah, blah, blah. Okay. So this is what it basically does is it lets you say, you could say default. So for any reason, if a contact forms, give it the linear model and give it this value of KN, KS, and fric. All right, default, everybody. If it's more sophisticated, let's say you have a box made up of 3 walls and you have sand balls that you throw in there and let them settle under gravity. Well, you might want to say, for the contacts between the grains, let's make that be a certain friction coefficient. But for the contacts between the interface of the wall and the balls, let's make that be frictionless. right? So what you can do is you can say, oh, for ball-ball contacts, do this. For ball, the walls are made of facets. So you say for ball facet contacts, do another thing. Okay. This is a completely general thing. So remember, I had that geogrid made up of balls, and then I had the yellow grains of the ballast, and those grains of the ballast were interacting with each other. So I had to use a CMAT to tell whenever the two yellow guys come together, do something, put a Hertz model in there. But whenever one of the yellow guys pushes against one of the blue guys of the geogrid, I just put a linear contact model in, because Hertzian model doesn't kind of make that much sense between a geogrid and a granular body. So that's an example of the use of this thing, and that's what we're going to do. And this is just giving another example. If I was trying to model some crazy thing like syrup that had these big nuggets in it, so what do I do? If the two nuggets push each other, I might make them bonded and make it brittle. But the syrup, like these guys, you could say, oh, that's going to be viscous contact model. And then you could say at the interface between the two, you have a different model, right? So this is the type of thing you can then do. It's a very general capability. In the manual, there's a tutorial example that's very nicely describes the behavior of this system and how to work with it. Okay, so that's what I wanted to say. That gets us to the end of the physics talk.